Alrighty, welcome back to Operating System. So, left off last lecture, we implemented a very crappy lock that didn't really work. We'll do better. So, let's get into it. So we can actually implement locks in software with actual minimum hardware. So the minimum hardware requirements are just, and I can't do anything about the volume, sorry, are just loads and stores have to be atomic and instructions execute in order, and those are the only requirements you need. So there's two main algorithms you can use. There's Peterson's algorithm and Lampart's bakery algorithm, which is basically trying to simulate that, like, I don't even know if anyone does that anymore. Go to a bakery, grab a number, and then you get served in order. So those are things you can do, but they are very, very slow. So they don't scale that well, and processors execute out of order, so might not actually be able to implement them. So there is this one magical atomic function we can assume that's actually done in hardware. Most of the time it's called compare and swap, and what it does is it takes an integer, well, it takes a pointer to some integer, and then takes a old value and then a new value. So the way this works is it will atomically compare the current, what's pointed to by that pointer, look at the value, and it will always return the original value pointed to, and it will only swap in the case that the old value is equal to old, and it swaps it to the new value given by new here. So it will only swap once, so it will essentially not make it possible for us to change 1 to 1. So this will only change a 0 to a 1, and it will return 0. So if we rewrite our lock implementation such that lock is just now while compare and swap, so L is just a pointer to an int, so point to that int, and we'll just do while 0, 1. And what this will do is it will only return 0 if it has successfully changed a 0 to a 1. So if it has successfully changed a 0 to a 1, it returns 0, and that means we can break out of the while loop. We knew we changed it from a 0 to a 1. And it will do this atomically in hardware. It is an atomic instruction. Otherwise, if the current value is 1, then it would just return 1, and we'd be in this infinite loop forever. And then unlock, we're the thread that changed it from 0 to 1, so there's no one else fighting with us. We can change it back from a 1 to a 0. So this is a valid lock implementation. It's not a very good one, but it does work, kind of. It's missing a few properties. It's not fair at all. It's not terribly efficient because even on a single core, even if it knows, you should know that it can't actually acquire it, it will go through that while loop over and over and over again while nothing else is going to change that value, but it does work. So what that is, it does have a name. It's called a spin lock because of that while loop. So if it doesn't acquire the lock, it will keep on trying again and again and again. That's where it gets the name spin lock from. So that compare and exchange, or compare and swap, is a very common atomic hardware instruction. On x86, it's called comp exchange, short for compare and exchange. Again, they have to make things very short for some reason, I don't know why. So this implementation still has a busy wait problem. That means that while a thread is trying to acquire the lock, it's just constantly wasting our CPU trying over and over and over again. So again, on a uniprocessor system, so system with a single core, if you can't get a lock, a better solution would just be to yield. So I yield, basically I give up my share of the CPU, let another thread run that hopefully has the lock so it can actually do the work, unlock, free the lock, and then I can go ahead and use it. On a multi-processor system, like if I have multiple machines, Maybe I don't want to waste the time doing a system call to yield myself. Maybe the critical section is so small it doesn't matter, in which case a spin lock might actually be a good thing to use. And hopefully it doesn't waste too much time spinning. So it has some use, and we'll see it has some use to actually help us implement something better. So our first thing, that if we want to make a more generic lock that doesn't have this busy wait problem, what we can do is in the while loop, if we do not acquire the lock, then we can just do yield, thread yield. But now we have another problem where there is something called a thundering herd problem. And what that means is multiple threads might be waiting on the same block, right? So if I have 8 threads waiting on it, then all of the 8 threads are going to attempt to get it, even though I know only one of those 8 are going to actually be successful. So I want something a bit smarter than this. And I also have no control over what thread gets the lock first, right? There's no actual line, it's not fair, so I need to be able to reason about the order threads actually acquire the lock in. Having something like first come, first serve, or FIFO is actually an okay thing to do. I just have to make sure there's some type of order. I cannot accidentally starve out a thread. So here is my proposed solution. So I am going to essentially come up with a wait queue. So assume I just have a queue, just be a list. I'll spare you the details. But now I'll change my lock implementation so that whenever I don't acquire the lock, so I go into the body of the loop, I would add myself to the wait queue. So say I'm going to wait for something, and then I'm going to, instead of yielding, I'm going to go to sleep. And what sleep will do is it will just block you until someone else wakes you up, and then you're unblocked again. So this was also a thing you had to implement in the thread lab before. You had to implement a sleep and a wake up, but I cut that for you, so you're welcome. But real threads will actually have something like this. So now in my unlock, to get rid of that thundering herd problem, I first change the value from a 0 or a 1 to a 0 to indicate that I have now unlocked the mutex. And now I could just simply check. If there is a thread in the wait queue, then I just wake up one thread. So I wake up one thread, and then when it wakes up, it would return from the sleep, and then only one thread would then again, at least that's the idea, do this compare and swap again and try and acquire the lock. Instead of having 8 threads do it all at once, I just have one thread. But there is 2 issues that we should get used to reasoning about due to essentially data races. So there are 2 issues. One is a lost wake up, which means, is it possible for a thread to get put to sleep and then never wake up? And then the other issue is the wrong thread gets the lock, because I should actually give the threads the lock in the order they tried to acquire it. So the first one is asking, is it possible a thread never wakes up? And the second one's asking, is it possible that threads get the lock out of order? So for the first one, to reason about it, well, first, you can't see what I'm doing, boom. So to reason about it, we can assume we have thread 1 and thread 2. So I'll give you some hints. You pretty much have to come up with a situation such that whenever these 2 threads execute, that one will never be woken up again. So let's assume that the lock is locked. So the current value of the lock is 1, and thread 1 has the lock. And then thread 2, here I'll put thread 2 in green. So thread 2 is going to try to acquire the lock. So it's going to call lock, and then thread 1, which has the lock, is going to call unlock. So, is there any possible interleavings of these threads which cause thread 2 to go to sleep and then never wake up again? Yeah.
I guess maybe we unlock it before we put it to the queue. Is it possible to do that?
We unlock it before.
Like the process ended, and we try to like check if a thread is in the queue before we actually added the thing in the queue. So that means we missed it. We missed the waking up thread.
So, yeah, what we're looking for is missing waking up a thread, so we can draw a wait queue here too. But what order causes that to happen? So one of these has to execute first. Let's just brute force it. Which one do we want to execute first, thread 1 or thread 2? Thread 2? All right, thread 2 executes first. So if thread 2 executes first, it changes the value of the lock from a 0 to a 1 to a 0. And then what?
And then it checks the queue, but we didn't put anything in the queue yet.
So, and then thread 1 executes again. So check the queue. There's nothing in the queue. That's fine. That's expected. Right? Nothing's in the queue. The other one hasn't started calling lock yet. So that's okay. Nothing in the queue, skips over. It's done unlock. Now thread 2 executes. Thread 2, it would do this compare and swap. Hey, luckily the value is 0. So it would change the 0 to a 1. Whoops. Why is this room so cursed? So change that 0 to a 1. Return 0, so it would actually indicate that it has locked it, and then it proceeds. So that's how it's supposed to work, right? So thread 1 unlocked it, thread 2 acquired the lock. That seems good. So that seemed to work as expected. Anyone think of a bad order things could happen in? Ow. Yeah.
Like, is it possible to, like, we try to wake up a thread when we didn't get a chance to add it to the queue yet?
So this means it would, yeah, so you're getting on the right track. You were trying to wake up a thread that hasn't added itself to the queue yet, right? Yeah.
What if the thread 2,
Mm-hmm.
you know, on that like comment line,
Yep.
thread 1 runs all the way through, and then skipped because there's nothing in the sleep queue yet, and then T2 puts itself to sleep.
Yeah, so the first thing that has to happen is T2 has to execute, right? So if T2 executes first, that means it's going to do this compare and swap first. So the current value of the lock is 1 because thread 1 has the lock. So that means compare and swap is going to return 1. So thread 2 is going to start executing the next line. So the next line it's going to go into the while loop. The next line it's going to execute is add itself to the queue. But now is when we context switch. So if we context switch right now, right before it adds itself to the queue, we context switch to thread 1. Well, what will happen is it will change the value of the lock now from 1 to 0. And then if it still continues execution, right now it would check if there's any threads in the wait queue. Is there any threads in the wait queue right now? No. So skip, it's done, it's unlock call. Now, if we switch back to thread 2, well, now it would add itself to the wait queue because that's the next instruction it is going to execute. So it adds itself to the wait queue, and then it goes to sleep. It has a little nap. Is anyone ever going to wake it up? No, it is now blocked forever. So that is an example of a lost wake up. So that is one bad thing that can happen. So that makes sense to everyone. We have come up with a bad situation that may happen that causes some unintended behavior that is not great. So, everyone agree with that? Yeah.
So, if another thread tries to come in and get the lock, they would get the lock, right?
Yeah.
And then when they go to unlock, wouldn't they eventually wake up this thread? Or?
Yeah, so it could be possible. So if that was the last thread that uses the lock, now it's blocked forever. But if another thread comes in, right, it would unlock and then maybe wake it up. But if another thread came in and put itself on the queue too, then there'd be 2 threads on the queue and it will only wake up one of those. So it depends. It's something that we may or may not see depending on how lucky we get. But there is a situation that bad things happen, which makes your life a lot more fun. All right. So everyone's okay with that till we get our next situation? So let's come up with a new situation where the wrong thread gets the lock. So let's assume, I'll help you out a bit here. We'll assume more or less the same scenario. So let's assume a scenario where we have, in this case, we're going to need 3 threads. So we have thread 1, thread 2, and let's assume thread 2 is properly asleep. So it put itself asleep because it couldn't acquire the lock. So thread 2 is currently in this wait queue. So if thread 2 is currently in the wait queue, that means it should be next in line, right? Okay, let's assume we have thread 3 that wants to get the lock. So it is about to call, well, it's starting to call this lock function. So is there a situation, and it just has to be one interleaving of threads, such that T3 steals the lock from T2? Can't even see the time. Yeah.
Like if the thread that unlocks gets interrupted before it wakes up the thread, it's interrupted by the new thread.
Yeah, so basically what will happen, there could be a situation where T3 steals it. If thread 1 executes first, then it would change the value of the integer from a 1 to a 0. Shouldn't be that. And now we can immediately context switch. If we immediately context switch to which one? Thread 3, right? If we immediately context switch to thread 3, then thread 3, before it checks anything, is going to come here, do the atomic or do the compare and swap. Hey, great, the value of the lock is 0. So I just change it from a 0 to a 1. And now thread 3 has yoinked the lock. So now thread 3 has acquired the lock. Now what's going to happen nothing bad is going to happen past this other than thread 3 yoinking the lock, because if thread 1 continues, what it's going to do is check if there's threads in the wait queue. So it would wake up one thread, so it would remove thread 2 from the wait queue. Whoops. So remove thread 2 from the wait queue, and then it would finish. Then thread 2 would return from the sleep, come back up here, do the compare and swap again, and then see that, oh no, the current value of the lock is 1, so it will just add itself to the wait queue again, and then take a nap again, so nothing that bad will happen in this case, just the wrong thread got the lock. So everyone understand that? Because you will have to tell me these things and come up with these situations. So I will probably ask you, hey, is there a situation where this may occur? You would either have to argue it's all good or come up with an example like that. All right, so just so you have it, there is the lost wake up example at the bottom there, just so you can go through it. And then the wrong thread getting the lock example, there is the situation there for you as well. So this is how we can fix the lock. So this is closer to the actual implementation of a mutex. So this, I submit to you, is the fixed version that does not have the lost wake up problem and does not have the thundering herd problem, and will not allow another thread to maintain the lock. So everyone like the look of that? Looks fantastic, right? So let's break it down real quick and let me know if there's any problems using this. So the whole trick of this is it uses that same idea. So we're going to have a queue of waiting threads that we're going to have in line. But we had some problem where we had essentially a data race problem before in our mutex function. So what we are going to do is we are going to use a spin lock to help us implement our lock functions. So this guard right here, this guard integer, we're going to use that integer essentially as a spin lock for the lock and unlock functions. So in order to make it a bit more readable, what you can do is this while compare and swap of the guard, well, you could get rid of that whole thing if you wanted, because that's essentially the same as just, that is way too big. So that's the same as just locking the guard. This room is cursed. So that's the same as locking the guard, right? And then at the end, whenever we set the guard to 0, and we do it in both sides of the branch, so we make sure we unlock it. So setting it to 0, boom, boom, to make this a bit more readable. That's the same as the unlock of the guard. So now in our lock function, we lock the guard so that only one thread can actually execute the code after it. So we don't actually need a compare and swap anymore for implementing the mutex, since we have acquired the spin lock, which we argue does work. It's just slightly inefficient sometimes, but this is really small. We don't need compare and swap anymore, so we can just go ahead and check. If the value of the lock is 0, we change it to a 1. Otherwise, if the current value of the lock is 1, we would add ourselves to the queue, and then we can unlock. Yeah?
So is this just to ensure that only like one thread at a time can lock or unlock, like without getting interrupted by another thread?
Yeah, so this is like that protected section we had before. So any code between lock and unlock, only one thread can be running it at a time. So we won't have the situation like we had before. So we can go over both situations as well. So here in the unlock, again, this compare and swap of the guard, well, that's essentially a lock of that spin lock. So to make it a bit more readable, I could just, that's the same as lock of the guard. And then at the end, this unlock, oops. This is an unlock of the guard. So now in the unlock, well, I acquire the spin lock, and I would first check if the queue is not empty, or if the queue is empty, then I just change that value from a 1 to a 0. If there is something in the queue, well, essentially the way this works is I just keep the value at 1, and I just wake up the other thread, which is here. I transfer the lock to that, and that will only wake up a single thread that is waiting, and the value of the lock is still 1, but one thread wakes up and then finishes that function, and now essentially I has transferred the lock to that thread, so now it can continue on its merry way. So, any arguments with this implementation? So, we can check to see if we can have that lost wake up issue again. So remember in the lost wake up issue, we had thread 1 has the lock, and then thread 2 was trying to acquire the lock, right? So in our lost wake up issue, what happened first is that thread 1 executed first, right? Thread 1 executed first and actually went ahead and changed the value of the lock. So let's see what happens if we do it now. Well, now the first thing we do is execute thread 1. If we execute thread 1 first, then it would lock the guard, so it's the only one that has the guard. And it would check the queue. Okay, it's empty. It changes the value of the lock from a 1 to a 0. So 1 to 0. And then now if we context switch over to thread 2 that had an issue before, now what happens? What can thread 2 do? Yeah, it can't do anything, right? Because thread 1 still has that guard spin lock. So it has that guard spin lock. So now if thread 2 tries to run, it can't make any progress, right? It's stuck there until thread 1 is done what it's going to do. So it's not done yet, it will get stuck there. And the only choice to make progress is to execute thread 1. So we've essentially prevented that lost wake up example, right? So now it would just go through, okay, change the value of the lock from 1 to 0, and then unlock. After it's unlocked the guard, then thread 2 can progress, and then it would just change that value from a 1 or a 0 to a 1 to indicate that it has that lock. All right, so any issues with this, or does it look like a very, what is the word, cromulent implementation? Is this a perfect implementation, work 100% of the time? Yeah.
Oh, we could get like context switch before the sleep.
Yeah. So there is one very, very subtle issue, but luckily it is detectable and fixable. If you didn't hear that, what that one very subtle issue is let's assume thread 1 has the lock again, right? So if we assume thread 1 has the lock and then thread 2 is trying to acquire the lock, what may happen is that, okay, if thread 2 executes, then it acquires the lock, the guard lock. It would come in here, check if the lock is 0. Currently it is not because thread 1 has the lock, so it would go in here, add itself to that wait queue. So we would have a wait queue up here. So it added itself to the wait queue, and then it unlocks the guard. Now we can freely swap to thread 1, right? So now we can freely swap to thread 1. Thread 1 can acquire that guard. Oops. It can now acquire that guard. Check if the queue is empty. Oh, currently it is not empty, so it should come here. And then it will try and wake up a thread that is not asleep yet. So, very, very, very subtle issue. The nice thing about this is, since there's no data race with the queue itself, it knows that thread is definitely about to go to sleep. So since it's about to go to sleep, it can just retry it a few times until it successfully wakes it up. So I spared you those details, but essentially this is a real implementation. The only other thing is that wake up would have to retry itself if that thread isn't asleep yet. Everyone good with that? Yeah?
Like, what will be the result of, like, we try to wake up something that is not asleep?
So if you try and wake up something that's not asleep, you just get an error saying that thread's not asleep yet. So in the real implementation, if you saw that error, you would just retry it because you know it's about to go to sleep. So subtle issue, but that's basically how it works. So have the slide that says, yeah, there's still a data race to explain that one situation. Okay, so we had the comment, I think, last lecture too. So remember what causes a data race, and again, I'm saying data race again, so you should know what this is. So data race, 2 concurrent accesses to the same variable with at least one of them being a write. So that means that even if there is a single write and it is uncommon, you have to protect the reads as well if at least one of them is a write. But if you know you have only reads, you can do as many reads as you want in parallel, right? So you ideally want to, if reading is really common and writing is uncommon, you'd like to have as many readers all reading at once as you can. And if a write happens, then you need mutual exclusion so you don't have a data race. So basically for that, you kind of want different behavior depending on whether you are reading or writing. So they came up with this other lock that has a very, very, very creative name. It's called a read-write lock. Wow. So a read-write lock, all it does is allows you to use the lock for 2 purposes. So you can either use the lock for reading, which will ensure that all the other threads are only reading, or you can lock it for writing, which will make sure that you are the only thread that has access to that lock now. So this is mostly for performance because reads can happen in parallel, again, as long as there's more writes. So multiple threads can hold the read lock all at the same time. Only one thread may hold the write lock, therefore we still don't have any data races. So an implementation of a read-write lock could look like this. So same idea as before. We have this internal guard just to make sure we don't have any data races. In this case, we don't want any data races. We're going to keep track of a field called number of readers. So other than that, we're just going to have this lock here. We're going to assume it's just a mutex. So if it's just a mutex, the implementation of the write lock and the write unlock can just be, well, just lock that mutex and unlock that mutex. While the read lock implementation is to simply lock the guard. So that guard is protecting accesses to this n readers, keeping track of how many readers we have, because we now know that plus plus n reader, that's a memory load and then a memory write. So it will increment the number of readers, then check If I have increased it from 0 to 1, this means it's the first reader, then I acquire that mutex. And then other than that, if I have multiple other readers come along, so if I increment it from a 1 to a 2, then I don't do anything, right? Because I already have the first thread already acquired that mutex, and I'm just sharing it because all we're doing is reading. And then at the end, I unlock the guard because that was just protecting the number of readers. And then in the unlock, all I do is lock that guard, decrement the number of readers, and if I'm the last reader, then I unlock that mutex. And then after that, I can unlock that guard because I was just using it to protect any writes or reads to this end reader variable. So, does that look like a good implementation, or is there some type of issue? And I will give you a hint. It works properly, but is it fair? Yeah. Yeah, you can starve the write. So no matter if one reader comes in and then a writer tries to acquire the lock, I can have a constant stream of readers come in such that the writer will never actually acquire it, even though it was technically second in line. So this would suffer from starvation. So I could starve a writer fairly easily. So this is the right idea. This is kind of how it works, except the real one would have to be fair, but that's boring to fit on a slide. But that's kind of the right idea. So they'd have to have a real implementation, probably want some type of queue to see when a reader or when a writer actually requests a lock, in which case it would probably block any more readers from happening, let the current readers finish, and then let the writer do it. But gets the same idea. We want parallelism for all the reads. We can have multiple reads happen at once as long as no write happens at the same time. So, any questions about that? Fun locks. That's basically how you implement a mutex and a read-write lock. Joy, everyone looks like they're about ready to have fun with another midterm. Yeah, that sounds about right. All right, then we will wrap it up quickly then. So we need critical sections to actually protect against data races. Critical sections, again, only one thread can execute at a time. It's always between the lock and the unlock. So you should know what data races are and how to prevent them. Mutexes or spin locks are the most straightforward locks. To actually implement locks, you need hardware support like that compare and exchange instruction or compare and swap. You would need some kernel support for thread sleep and thread wake up. And then, you know, if we have a lot of readers, you should use a read-write lock. Again, that will be for performance if you actually want your program to actually run in parallel when you have multiple threads. So just remember, poem for you.